All right, well, Isaiah, Dave, welcome. Just finished my appointment. I'm in the process of closing the house, and they had to schedule the winter inspections today between our work here. So that's why I needed to extend this time, because initially I was not going to do it, but they told me, yeah, you won't get paid. So I extended it. With a new house coming up, not getting paid is not a choice. Anyway, thank you for showing up. I will record this, as you probably saw it, heard this recording. We're going to go over chapters 5 and 6, probably for sure, and then maybe touch on 7. It depends on our time and so forth. So let me share any questions before I proceed. Feel free to jump right in there. You got a question, okay? All right. What do we got here? Okay, so anyway, up to this point, we got somewhat of a model of how atoms are put together based on the work done by Rutherford and J.J. Thomson and so forth. Our model at this time is that the atom consists of a nucleus, which houses the proton and the neutron, okay? And then the electrons are somewhere around at this point. We don't know exactly what's going on, where they at, and so forth. We don't really have a model to explain it up to this point. However, it was observed that if you take an element or any compound and put it in a glass container, much like a fluorescent lamp or fluorescent bulb or neon light, if you take that and subject whatever you put in that tube, run it through run some electricity through it, it would excite the molecules. Now remember that we talked about the relative mass, the AMU of an electron. It's given a value of 1. The proton and neutrons are the heavy boys, and you get an AMU of 1, atomic mass unit of 1. Electrons are basically, they're so small, they basically have an atomic mass unit of 0 because being so small. The fact that they're small, they behave like light. They have light behavior. And it was observed that if we take, I'm going to talk about it here in this chapter, if you take that light emitted from that tube, that fluorescent tube, and you run it through a prism is just basically a piece of glass, a little more to it than that will separate the light into the different wavelengths. We all know about or heard about wavelengths of light. When you see a rainbow, for example, after it's rained and it's got the colors there you water droplets have taken that light and broke it up into the different wavelengths, and hence we see the rainbow spectrum, okay? Or what we call the electromagnetic radiation. Now, the term used, electromagnetic radiation, people correlate that with bad electricity, or not electricity, bad radiation, bad X-rays, and that's true. But that's only part of the electromagnetic radiation. Our visible light is part of the electromagnetic radiation, very small. Even radio waves, we'll talk about those here in a bit, are part of the electromagnetic radiation. So what happened was, after we took that element in that glass tube and analyzed the light that it emitted, it broke it up into different spectrum. And that is where the picture started to show up that is these lights, or this emissions line spectrum, is where electrons exist. The bottom line is this, that electrons exist in very specific energy levels, okay? If you look at the periodic table, there are 7 horizontal rows. We call those periods. The model tells us that there are 7 energy levels, much like the layers of an onion, if you will, as an analogy. We got the first layer, which is the very first period number 1, which encompasses hydrogen and helium. Okay. And then we go to the second one, which encompasses lithium all the way across to neon, second energy level. But it just turns out that these electrons exist at very specific energy levels. Okay. Very specific energy levels. And we'll get more on that here in a bit. Before I do that, what I'm going to do is talk about light, because to correlate how the electrons are behaving, because electrons behave much like light. And our model for light is that light exists as waves. And so electrons being as small can also exist as waves and exhibit wave properties. Okay. And so this diagram here kind of represents a wave of light. So you can see here this curve where it's traveling, like so, represents light propagating through space. Okay. Now, if we look, and this consists of hills and valleys. Here's our wave. Okay, here the book uses trough and crest. But if we take a spot on the first hill, and we were able to measure the similar spot on the next hill, okay, that distance has a specific length, and it is called a wavelength, and it has the symbol of, this is lambda, the Greek symbol for wavelength, okay? And so the wavelength has that symbol. And these wavelengths have specific distances. It could be nanometers, 10 to the negative 9 meters. It could be micrometers. It is a specific measurement, okay? Now, the frequency here, we talk about the wavelength, and I just described that. Now we take the top of the hill, but keep this in mind. You can pick any position on the first wave as long as you select the same position on the next wave. So if I were to say mark this spot, guess what? I need to mark the same spot on the next wave, and guess what? That distance is the same as if they were on top of the hill. The wavelength remains the same. Or I can pick the bottom of the hill. Okay? Also, that is the same wavelength, the length. Okay. So normally, by convention, we pick the top of the hill from hill to hill. Now, within a given time unit, which is normally a second, if we are able to measure how many waves occur within a given time unit, we have what is called a frequency. And that symbol looks like a V, a little bit of a fancy V, and that is called a V. Excuse me, it's called the frequency, and that is how many of these wavelengths occur within a given time, which is normally 1 second. And you may have heard symbols like, well, let me do, this has units. This units is called hertz, okay? Units of frequency are called hertz. And you may have heard it if you went out to bottom of your computer and they tell you, oh yeah, your processor operates at say 2 gigahertz, okay? And that is, it operates at a speed that not 2 gigahertz, 2 billion things are occurring within a given second. Pretty fast, okay? Pretty fast. So that's frequency. That's just how many wave cycles are completed within 1 second. So we've got wavelength and frequency. Here represents, we have a diagram of 2 different wavelengths. You can see that the top one has a very long wavelength compared to the bottom one, which is wavelength is a little bit shorter. See, here we got the top one, okay? And here we got the bottom one with a very short wavelength, relatively speaking, to each other. Now, when you have a very long wavelength, or a long wavelength, doesn't have to be very, but a long wavelength relative to a short wavelength, the long wavelength has a low energy. And within a given time unit, it has low frequency. So let's say, for example, that distance from here to here was frequency, right? You can see that we got, you know, two hills and one valley running through the top one, whereas the bottom have a lot more. Okay, more wavelengths have occurred within that given time of 1 second. And so that means the top one is a low frequency within a given time unit of 1 second compared to the bottom one, which has a high frequency. Okay, so a short wavelength has a high frequency, long wavelength has a low frequency. Electromagnetic radiation has associated with it an energy component. Okay? So it has a specific wavelength, but also associated with that wavelength has a specific amount of energy or light energy here. So long wavelengths have very low light energy, and high wavelengths have short wavelengths have a very high energy. A good example here would be, let's say a long wavelength would be radio waves. Radio waves, very big wavelengths, in the meters, 7, 8, 9 meters, very big, okay? They're not very powerful. In fact, you know, if you listen to the radio, if you miss, you know, if you're getting bad reception, it's probably because the radio waves are being blocked by, you know, objects around you. On the other end of the spectrum, a good example of high energy would be X-rays. X-rays have very short wavelengths, okay? And having short wavelengths, they have a high frequency. More importantly, they have a high energy. High enough energy that they will penetrate your skin, your body, and hence you can take an image of your body, take an image of your bones, okay? X-rays is a good example, and even more powerful than that are what are called gamma rays. Those are even stronger and more deadlier. Okay? All right, so the takeaway from here is long wavelengths have associated with it low energy and low frequency. In contrast, short wavelengths have associated with it high energy and high frequency. All right, so you could be given a diagram like this and you're asked a question, which wave has a higher energy? Well, obviously, based on this, the one with the shorter wavelength, and you can see that B is a shorter wavelength. And the lower frequency, that would be A, okay? All right. Now this electromagnetic spectrum, is shown as follows. There's a spectrum. On the far right, you have radio waves, same radio waves that you're familiar with respect to free music on your vehicle, okay? You're picking up the radio waves. Associated with it, very big wavelengths. On the other end of the spectrum, you have gamma rays associated with it, very short wavelengths. Our ability is in this little spectrum. Now this spectrum is not to scale, okay, obviously, because if we have one to scale, and we got the radio waves and the gamma rays on each side, what we see is a very short spectrum. We are limited because our eyes are only there's two types of cells in our eyes, or what they call cones and rods. The cones pick up this wavelength, the visible wavelength, and the rods are more associated with kind of grayscale. Okay, and we have a very small spectrum of what we can see. Below visible, we have of less energy is the infrared. And then, of course, the infamous, you know, how to zap your popcorn, the microwaves, and then the radio waves. Above visible, you have a lot more powerful UV, ultraviolet. Ultraviolet can be hazardous, responsible for a lot of sunburns out there, responsible for a lot of skin cancers and crop damage out there, okay? And then, of course, X-rays. So be familiar with the spectrum: gamma, X-ray, ultraviolet, visible, infrared, microwave, and radio waves. So, okay. Now, in the last chapter when we talked about J.J. Thomson and Rutherford and Chadwick, and Chadwick was more in the 1930s. But the models of how atoms are put together really start coming together around the 1900s. During this time period, there's a number of scientists working on this, and scientists just as bright as Einstein. This is also the time period that Einstein did his work. Okay, you have Max Planck, 1900. Max Planck, very famous German scientist. There's a Max Planck Institute in Europe named after him. He proposed a very controversial idea at the time. Excuse me. He proposed that energy was emitted in small bundles, okay, of which he called quanta. So these bundles of energy were emitted. 1900. I remember we got J.J. Thomson. I'm having a senior moment with the other guys, but J.J. Thomson, but they're just some of the scientists. We have Schrodinger, we have so many other guys. So what he's proposing, that energy is not continuously emitted, okay, and that each individual unit of energy, each quanta, he just defined it as a photon. Now, light can be very powerful. Light has a lot of energy associated with it. There are lasers out there that have the capability of cutting metal. There's a lot of energy, okay? And so it may not seem that way, but if you set it up properly, you can have this light cut stuff, okay? So anyway, photon, also known as photon torpedoes if you're a Star Trek fan. All right, so energy is quantized. They exist in specific energy levels, not continuous. And the best way to describe that is by this wedge. Here we got the one on the left where the walls are rolling down this wedge. It's all continuous, okay? And whereas quantized, each is depicted here on the diagram on the right with this person climbing up the steps. Every step represents a specific amount of energy, okay? So we have at the bottom, at the ground level, that is our ground state. I'll be using that term a lot, ground state. That is the most stable state of, let's say, an electron, okay? And if I give it energy into the system, either by heat or either by electricity, energy in general is going to excite that molecule or excite that atom and excite that electron. And that electron that could exist and will exist in the electron in the ground state, guess what? Gets kicked up to the next energy level, which could be the first step, okay? Now, what happens is, Mother Nature being Mother Nature, when a molecule is up in the excited state, it cannot hang there forever. It must drop back down. And when it drops back down, based on the conservation of energy, the law of conservation of energy, that amount of energy that has to be released. And that same amount of energy that you put into the system has to come out. So if I put in 10 units of energy, when it comes back down to the ground state, it's going to release 10 units of energy. Energy will be released either as light or even as heat. Okay, if you have an electric stove at home, you turn that burner on, that metal piece warms up. And it starts to warm up, you're going to notice that the burner will get hot. Okay, because electricity is running through that metal and it's exciting those molecules. And those molecules can't hang there for a very long time period. They go back down and it has to release that energy, and it releases that energy, in this case, as heat. fluorescent bulbs, lights are doing the same thing. In fact, that's the screen you're looking at right now is what's happening to the molecules on the surface. They are accepting energy from some source, and they are then releasing it as light, okay? All right, so we have very specific energy levels. Now, another scientist, Niels Bohr, he proposed that the electrons orbit the nucleus, which kind of at the time people had an idea that's what's happening, okay? Because we already determined to get a proton positive in the front, in the center, and electrons negative are somewhere out there, outside, maybe orbiting like the planets are. Okay, but he proposed that these electrons orbit around the nucleus and occupy orbits with very specific energy levels. So as light was being quantized, he proposed that electrons are also quantized. Okay? The electrons orbit the nucleus, kind of like the planets orbiting the sun, but not in two-dimensional, because we're operating in three-dimensional. So these electrons are in three-dimensional mode, not like our solar system, where it's just really two-dimensional. Okay. Excuse me. These orbits, which we call energy levels or shells, you may see the term shells. The periodic table shows them. Let me share with you my periodic table. Now, if you notice on this periodic table, I got listed in blue. I got on the far left, I have the numbers 1 through 7. Okay. So you might want to take your periodic table, and a lot of the periodic tables have that number. This one does not, but it's 1 through 7. Those represent the 7 specific energy levels of electrons. Okay, we're going to learn that not only do we have these 7 energy levels, that within the energy levels, we're going to have what we call suborbits. Okay, sub-energy levels, which are called orbits. Okay. Very specific type of orbits. Okay, so every orbit has a specific radius and a specific energy associated with it. Okay? And because the specific energy is a specific distance from the nucleus. It is shown here in this diagram, denoted by the circular dotted lines. Keep it in mind, this is more like the orbits of our solar system, but we're three-dimensional. Okay, we're showing you a two-dimensional picture, but think three-dimensional. These orbits are all round. If it's orbit number 1, it's all around the nucleus. Okay. Now, how do we know this? What's happening here? Why did we come up with this particular model? This is shown by what is called the line spectrum. Okay. Basically, Bohr realized that taking a gas or an element and putting it into a glass sealed and vacuumed, basically make a fluorescent tube, it will give off light. Okay. And that light then is passed through a prism, which then separates the light that emits, and what we generate is what is called an emission line spectrum. Okay, and here's the diagram here to show you what's going on. So we have the gas in the sealed glass tube. Okay, and we have a charge running through it. All right, we emit it, turn it on, it emits light, and so we just take some of that light and we just run it through some slits, and all that's doing is just focusing the light. Okay. And it's going to focus it into a prism. Well, the prism light goes in and comes out with different lines because it's separated, just like the rainbow that we see. It's separated into specific wavelengths. Here's the numbers of wavelengths for this particular gas. This happens to be hydrogen. Okay. And NM is the units for nanometers. Okay. So we end up with these spectrum lines. This is very unique to hydrogen. In fact, that's how we can identify molecules, because this is a fingerprint. The line spectrum, this one that we observe, is a fingerprint for hydrogen. So if we do any analysis of light, we can determine here on Earth or out in space, if hydrogen's in there by analyzing the light that's emitted. Okay. If we do a number of different elements, we end up with a totally different line spectrum for each one. Yes, there may be some similarities because maybe they share the properties of certain electrons, but definitely separate, different, unique for each one. So we've got lithium and sodium here, potassium, all right? And that is the specific wavelength. So each element produces a different emission line spectrum, and it's a unique spectrum. And as I explained earlier, is what's happening here is denoted here in this model, where we have this would be considered, say, the ground state. This is the ground or the stable state. So we have the nucleus, and then orbiting around the nucleus, we have an electron, okay? Well, then what happens is we put energy into the system of some sort, heat, electricity, and so forth. And guess what? The electron gets kicked up to the next energy level. Here existed in the first energy level, and it gets kicked out to a very specific amount of energy is absorbed, and it gets kicked up to the next energy level. Mother Nature being Mother Nature, it cannot hang up here in the excited state. This would be the excited state. Okay. Okay, because it's been kicked up to the next energy level. It drops back down from the excited to where it was originally, the ground state. And in the process, has to release the amount of energy it took to get it up to the excited state. And it will release it, in this case, most of it as light. Okay, and there's some heat. Okay. All right. And very unique. That distance from the first energy level to the second is very, very specific. Very specific. All right. So there are 7 energy levels. Okay. Now this model that's come about that I'm going to talk about, this model arises totally from a mathematical equations. This is an area called quantum mechanics, which is way beyond the scope of this class, and definitely not going to touch into it. But it's very, very sophisticated mathematics to explain the electrons that orbit around the nucleus of all the elements. So we have at this point, we have 7 energy levels denoted by the numerical numbers 1 through 7. Within the energy levels, there are sub-levels, which I will be calling those orbits, okay? Orbits. Now, not all of the energy levels have all of the orbits. For example, we got 1, 2, 3, 4, 5, 6, and 7 energy levels. Okay, the first energy level only has what is called the S, denoted by the letter S. There are 4 different types of orbitals. S, the P, the D, and the F. Okay. Now I'm going to throw another number for you. There are only number of orbits. There's only one S. Simply, that's it. There's only one S orbit. The P's, there are 3 S orbits. The D's, they're all P's, but there's 3 of them, okay? The D's, there are 5 of them, all 5 D's, okay? And the F's, there are 7, okay? So for the S, there's only, for the S, only one S orbit. P's 3, D's 5, and the F's 7 of them. Now for the first energy level, which really encompasses, if you have your periodic table next to you, you have hydrogen and you have helium. That's it. Those are the two elements that utilize the 1s electrons. The second energy level, which starts from lithium all across through neon, there are two types of orbits. We have the S, and let me note this. All seven energy levels all have the S orbit. The only difference between a 1s and a 2s and the 3s and the 4s is their size. So the first energy level is, this diameter. The second energy level is this diameter. The third, the fourth, the fifth, etc. Okay, but they all have the same shape. Okay. So the first could be maybe the size of a ping pong, to give you an analogy. Second energy level, now you're the size of maybe a baseball, and so on. You go up to maybe a beach ball, and so on and so forth. Okay, but the different sizes. The P's don't come in until the second energy level. And guess what? Everybody from after, starting from number 2 energy level down, have the P. So you got the 2P, the 3P, the 4P, the 5P, the 6P, and the 7P. All right. And again, the only difference between the 2P and the 3P orbits is the 3P orbits are bigger. That's it, because it's second energy level. Now, in the third energy level is where one introduces the D orbits, okay? The D. And so you got the 3D, the 4D, the 5D, you got 7, and the 6D at this point. We stop at the 6D simply because we only have 7 energy levels and we only have 818 elements. Once we get more than that, and then we can end up with a 7D, but right now we're looking at 6D. All right. Now, in the fourth energy level, this is where the F orbits come into play. And so, yes, we have the 4F, the 5F, and at this point, that's where it stops. Not until such time that we get a lot more elements, okay? And you'll see here for a second why that's the case. All right. There's something else. Now, we denote each energy level with the coefficient 1, 2, 3, 4, 5, 6, 7, followed by the letter. So if I wanted to denote the 1s, I would say 1s, okay? If I need to go to the next level, it would be 2s. I'm going to write them out like this. And P will be 2P, okay? The coefficient represents the energy level, and the letter S represents the orbit, so, okay, for that energy level. Now let's take it one step further, one more bit of information. I mentioned here, up in here, that there's only 1S, 3 Ps, 5 Ds, and 7 Fs. Now, every orbit, regardless of what it is, S, P, D, or F, can only hold a maximum of 2 electrons, okay? And so the S, P, D, and F, the number of orbitals was like I wrote, 1, 3, 5, and 7, okay? Now, every orbit can only handle 2 electrons. So the 1s can handle a maximum of 2 electrons. Okay, max 2 electrons. The P's, because there's three of them, three separate ones, each one can handle 2 electrons, can handle 6 electrons total. The D's, there's 5 separate D's, each one handling 2, gives me a total of 10 electrons. And then finally the F, with 7 individual F orbits, can handle a total of 14 electrons, okay? So that is a maximum for each particular orbit. And what we do is we write as a superscript for that orbit the number of electrons that it has. And so let's assume for the moment that 1s is maxed out. So the superscript would be 1s2. That's 2 electrons for the s. Remember, the s can only handle 2 electrons. And sometimes I would write it 1s2, but if I only have 1 electron, I can write it as 1s1. What I'm doing here is to introduce you to electron configuration. And what that is a means to write out the number of electrons for an element. Not only, and that would tell you what energy level the electrons are in, and it would tell you what orbital they're in, and it would tell you how many electrons in each orbit, okay? And that's called the electron configuration. So the next level, let's say 2s, let's assume that it's maxed out. I can put a 2 there, superscript. But the next one now, the P, remember the maximum I can put is 6 electrons in the P's. Well, I could.
So I got a question.
Sure,
Sorry.
go ahead. No, go ahead.
So when we're writing the levels of the electrons in their valence shells, I noticed that a lot of like videos that I've seen on YouTube, they represent each level with the noble gases. Oh, is that something we're going to learn as well?
Oh, yeah. That's a shorthand way of writing the electron configuration. And okay. I'll introduce that, because first I'm going to show you how to write it, the electron configuration longhand, okay? Then from there, once we learn what the noble gases are with respect to their electron configuration, we can take the electron configuration and use that to demonstrate, okay, the electrons, have all of neon's gases, and then I got to add more to the right of that, okay? And that's a shorthand method to write the electron configuration. But right now we're going to, sure, no problem. We're going to go and learn how to do the longhand, and that's what we're doing right now. So I haven't correlated which element I'm writing here. I'm just showing you at this point how to write the electron configuration with the coefficient, which represents the energy level, and then the letter, which represents the orbit that you'll be utilizing. And then you use a superscript to represent how many electrons it has for that particular orbit. So right now, this electron configuration is a 1s2, 2s2, 2p1, okay? Now, with time, you will be able to look at the electron configuration and actually tell me which element that is, okay? All right, so I say P1, but maximum P electrons you can put in P is 6, so you could have it go all the way to P6, okay? Now, the second energy level can only has the P and the S and the P. So if I pick up another electron because I'm going to the next element, guess what? I cannot put it in the second energy level anymore. I got to move up. I got to put in a new energy level, which would be the 3s. And then if I got to add one more electron, I add 1. Okay. Now, that is the longhand way of writing the electron configuration. I will show you what the book tells you and how to use this sequence of writing them in, but I prefer, and I will show you how to just use the periodic table and the position of the element in your periodic table so that you can look at it and bam, that quickly write the electron configuration rather than having to memorize this sequence of filling up the energy levels. Keep in mind, we are simply just building up the energy levels when we add electrons. So hydrogen begins here. If we want, this is the very first, this is hydrogen. This is the electron configuration for hydrogen, 1s1. It is the very first element. It has a element number 1, got 1 proton, 1 electron, right? And it's in the first energy level, boom. And it's in the first column of the periodic table, which also tells me how many S's, how many electrons are in that S orbit. But just to show you, that is the electron configuration for hydrogen. And if I go across to helium, what am I doing? I'm just adding 1 more electron. And that is helium's electron configuration, because helium's got 2 electrons. And then I wrap around to go to lithium, and it's the 3rd energy level. We're going to do some examples, okay, how to utilize the periodic table to write out the electron configuration. So right now, talking about the orbits, how many electrons can fit in the orbits, talked about the different energy levels here, and where the orbits begin, okay? The 1 energy level, there's only 1, that's it. The S. 2nd energy level, the S and the P come into play. 3rd energy level, the S and the P and the D. And the 4th, we got the SP, D, and F come into play. Okay. Now, if you're ever asked the question, what is the maximum number of electrons can the D have? Well, that's the answer right here. Okay, there's 5 Ds, each one can handle 10 electrons. Or you could be asked the question, well, what is the maximum number of electrons that I can put in the 2nd energy level? Well, to answer that, you have to know the 2nd energy level has the S and the P. So you know that the S is maxed out at 2 and the P is maxed out at 6. That means that the max electrons for the 2nd energy level would be 8. 8, right? All right, you might be asked, well, what is the maximum number of electrons that I can put in the 3rd energy level? Well, again, the S is maxed out at 2, the P is maxed out at 6, and the D is maxed out at 10. So 10 plus 6 plus 2 is what? 18. 18 electrons is the maximum number of electrons that I can put in the 3rd energy level. What about the 4th energy level? What is the max number of electrons that I can put in the 4th energy level? I'm going to take a gander, take a shot at that. What do you guys think?
32.
Got it, exactly. So 32 is the maximum number of electrons I can put in the 4th. I didn't say the total. If there's an element that exists in the 2nd period, okay, that just, you know what its atomic number is, you know how many electrons it has. But if you really think about it, I got 6, 2, and 2, that's 10 electrons. Guess who that represents? Who do you think has a total of 10 electrons? Wouldn't that be neon?
Yeah.
Neon, exactly. All right, but more on that, we'll come back to that in a second, okay? So let's move on and kind of put everything together. Right now, it's probably clear as mud. All right, so this is a rehash of what I just talked about. The 1st energy level has 1, that is the S, okay? The 2nd has the S and the P, and then the D's come into play. Now, at this point, the 4th energy, that's where the F's come to play. Where the confusion sits, okay, which hopefully is not too confused. Notice that we start off in the 3rd energy level, D. The thing to take away from that is that these 3D electrons come from the elements that are in the 4th period, okay? And they only start with element number 21. Okay, now you might say, well, let me add something to that. Back to the periodic table. Notice my periodic table here. Okay, I first introduced and said, if you don't have a number on it, 1 through 7, I would put that down so for your reference. But on top of that, if you look, I got S elements in blue, D elements, P elements, and F. Well, let me explain. When you look, also to look on the column of the elements, for example, 1A, the very first column, it says 1A. Next column is 2A right here. Oh. Here it is. We have this, that's a 1A right there. 2A, okay? This is only true for the A elements, the Roman numeral A, okay? And then we got the 3A and the 4A all the way to the 8A. That Roman numeral is going to be very helpful, okay? Because what that's going to tell you is that Roman numeral and that element in that Roman numeral is how many what are called valence electrons exist for those elements in the same column. So hydrogen on down, everybody in that column, though they have different number of electrons, you know, lithium has 3 electrons. Lithium's number 3. Sodium has 11 electrons. Yes, they differ in the total number of electrons. But of those 3 electrons for lithium, one of them is in the outermost shell, which is the valence shell. And that outermost shell happens to be in the second energy level. Sodium, the one below it, has 11 electrons. Of those 11 electrons, one of them is in the outermost shell, which happens to be in the third energy level. And that's what lithium and sodium and potassium and everybody share, is that they share 1 electron in the outermost shell. And when it comes to chemical reactions, all the action happens on the outermost shell, not the innermost electron, but the outermost shell. And that is why everybody in group 1A react very similar, because they have 1 electron in the outermost shell. Okay. Now with that trend, Roman numeral 1, what could you say about these elements in group 2A with respect to their valence electrons? What do they all share in common? How many valence electrons do they all share?
They have 2
You
on
got
their
it.
outermost shell.
2 on their outermost shell. Now let's take it across here. We can't do this. We can't do this with the B. Those are in here, the D elements right now. You can't do that with, but all the A's you can. If you go into group 3A, what they all share is 3 valence electrons, and 4A, 4 valence electrons in outermost shell, and you can get the gist of it. That means that everybody on the far right, except for helium, because they only have 2 outermost shell electrons, but neon down, they have, guess what? Any idea how many valence electrons they have? The ones I highlighted in the green box?
They have 8.
You got it. 8 is that magical number we're going to be talking a lot about. 8 is that number by which these elements want to strive for to obtain stability. And they're going to strive that by either gaining electrons to give them 1 more electron to get 8, or by losing electrons. So the next shell in is full with 8 and they're a lot more stable, because they're trying to strive to be what we call isoelectronic with a noble gas, meaning they want to have the same number of outermost shell electrons than the noble gases. And the noble gases are very stable. They don't react very readily. And that is why, because their outermost shell is full with 8. Putting an electron in only will make that electron go to the next energy level because the outermost shell is full for the noble gases. So from an energy perspective, it's not very liable. Can it happen? Yeah, sure, anything can happen. Don't let them lie to you. There's nothing 100%. It can happen. The probability of it happening is very low. Okay. All right. What about removing the electron? Well, guess what? I got 8 electrons all being held tightly by the protons because I'm in a stable state. So it's going to take quite a bit of energy to pull one electron off. And there's a property for that, which is part of one of the chapters. Because obtaining that magical 8 is the key. Now, let me regroup here for a second. I labeled what we call the S elements, and that's for groups 1 and 2. So if they happen to be in those groups, think of them as the S elements. And look at this, there's 2 columns in the S elements. And how many electrons can we get in the S elements? Only 2 maximum, okay? Let's go jump over to the period 3 forward. If you look at this, guess what? Count the number of columns that you have, starting from boron to neon. You should count 6 columns, okay? And think of those elements as the P elements, P. And we said that the P elements, the P orbitals, there's 3 of them. Each one can handle a maximum of 2. So we can have a total of 6 electrons for the P element, for the P orbitals. And guess what? P1, if you think about this, P1, P2, P3, P4, P5, guess what? P6, right? I'm trying to write S1, S2. Okay, and that's when I'm adding the electrons to the p orbit. And that doesn't kick in until I get to boron. Before boron, I got lithium, beryllium. I'm not worried about the p's until I get to that element. And so we'll do some examples here in a bit. Now, the ones labeled D, D as in David, think of those guys as the D elements. And these are the ones here. Okay. And there should be, guess what, 10 columns in the D elements, starting with number 21. And if we were to label the electrons, it would be from, D1 all the way across to D10. Okay, to zinc D10. And then down at the bottom, what we call the F elements. Okay, there should be 14 columns there. Okay, remember there's 7 F orbits. Each one can handle one electron, so it can handle a total of 14 F electrons. So starting from the far left, F1 all the way across to F14. Okay, and that helps us knowing who are the P elements, the D elements, and the period they're in, helps us very quickly write an electron configuration for literally any of the elements, okay? But now I'll come back with some examples of that. I want to continue with what the book is telling you here, okay? Right, these are the orbits again, shown 3-dimensionally, levels, the energy levels 1 through 4. And the respective orbits that we just talked about, all right? So orbits are nothing more, keep in mind, these orbits come from mathematical equations, come from quantum mechanics, extremely sophisticated field. Mathematics, literally all mathematics. And when these orbits were developed, what it was just a equation, mathematical equation. And you can take a mathematical equation and plot data to it, and you end up where they plot. So what's happening is that you got the plot of that orbit, and you get a particular shape, okay? And we'll have some pictures of that. We talked about this. We said the S has there's one S orbit, 3 Ps, 5 Ds, and 7 Fs. Each one can handle 2 electrons. So the far right column represents how many, what is the maximum electrons for the orbits, not the energy levels, but only for the orbits. So 2 electrons, 6, 10, and 14 respectively. Okay. Now, one way to look at this is by this pyramid, but in reality, I keep meaning to flip this period upside down because that's what you're doing. You're putting electrons into an element from the lower level and then building up. Okay, so imagine that in your mind that you flipped it up, starting with level upside down, and you got an upside down pyramid. All right. Now, you have energy level number 1, which encompasses hydrogen and helium. Okay, if you have your periodic table there, you can follow along using correlate this with the periodic table. Each box represents the orbit, and in each box, I can put an electron. Okay, so I'm going to use red here. So if we get the first energy level and we got hydrogen, I'm gonna just draw a dot. Okay, that dot represents the first electron, which is hydrogen. Okay, now as I continue across the periodic table, I get to helium and I can put a second dot. Okay, normally these boxes you put arrows, but I'm not going to make them a dot. Normally, if this was an upper level chemistry class, we'll put an arrow to demonstrate that when you got 2 electrons in a same orbit, one orbits one direction and the other one orbits another direction. And it's really fascinating. If you could change the orbit of one electron, automatically the other one gets flipped. And nature handles it automatically. So now you have the 2 electrons, you're maxed out, and you're at the far right of the periodic table, which is helium. Okay, that would be how helium would have its electrons. They'll be in the first energy level, and it'll be in the first orbit. And so its electron configuration for helium will be simply 1s superscript 2. Okay. Now, as we go across to around the periodic table to the beginning to number 3, okay, number 3, we can't put the next electron anywhere in the first energy level because we don't have any orbits there other than the s, and they're maxed out. Okay, so you have to go to the next energy level, which is the second energy level. Now, the sequence of filling up the orbitals go as follows: S, P. So I'll go down here. You fill the S first, followed by the P, then the D, and then the F. Okay, when you have more than one orbit, you don't fill up the P, simply because within the energy level, the S is a little bit less in energy level, lower energy level than the P, so that gets filled up first. Okay, so that is lithium. And if I had the next one would be beryllium, that I can put my other dot there in the S, and that's beryllium, number 4. Okay, as I go across the periodic table, remember now you hit the P elements, the very first one, which is boron. It's a P. It's the first one in the P element column. And if I put that, so that would be 2s2. So I could write 2s2 to designate that's full. Here I can write 1s2 to designate that's full. And here I can write 2p superscript 1. And that represents boron. Okay. Now keep that and go across the periodic table. There you got carbon. Got one more electron, right? Carbon has a total of, where's that for? 6 electrons. Okay, so then this would be written as 2p2. Okay. Look at the group that carbon's in. It's in group Roman numeral 4a. That tells you it has 4 valence electrons. Valence electrons are the outermost shell. These dots represent the electrons. Of those 4 valence, it has 6 electrons, but 4 of them are in the valence shell. Of those 4 electrons, 2 of them are in the p orbit and 2 of them are in the s orbit. Okay, so we got carbon. Let's go to the next one. That is nitrogen. Guess what? Nitrogen is in group number 4A. Excuse me, 5A. Okay, 5A tells you I got 5 valence electrons. Do I not have 5 valence electrons here in the second orbit? I got 2 in the s and 3 in the p. Now notice I fill up each individual box first before you double up. Okay, that's just part of the mathematics involved. So right now you're at nitrogen. Now go over to oxygen. Oh, that would be a 3 here for nitrogen. Okay. Now you go to next one, oxygen. You pick up 1 more electron. Which box I put it in makes no difference. Okay. Remember that you can only put 2 in each box. So that 4 now becomes 3 becomes 4. What am I saying? It's in group 6, oxygen that is. It has 6 valence electrons. 4 of them are in the p orbits and 2 of them in the s. And I want you to start thinking about this, okay? Oxygen and nitrogen are non-metals. So 2 things to remember and put in long-term memory is this. All metals, remember that slide to show you which elements were metals? It was color-coded. All metals lose electrons, okay? All non-metals gain electrons. Nitrogen and the oxygen here are non-metals, okay? They have a tendency to gain electrons. And why? Because by gaining specifically 2 electrons, they fill up the 2p orbit and makes it stable, okay? So it ends up gaining 2 electrons with a -2 charge. Nitrogen had a -3 because nitrogen, the one previously, would pick up 3 electrons, okay? Carbon, who have 4, is sort of on the fence. Carbon has the capability of losing 4 or gaining 4, any combination thereof, okay? But after you pass that, after you pass carbon, anything before carbon lose electrons, okay? Because they're all metals. Anything after carbon gain electrons from the non-metals. And the number of electrons they gain depend on what group they're in and how many electrons they need to fulfill that magical 8. Okay, so you got oxygen here. Now look at fluorine. Fluorine, let me erase this, make sure I write it properly. The electron configuration of fluorine is as follows. 1s2, 2s2, 2p5. Okay. Fluorine is in group 7A. It tells you there's 7 electrons. And don't we have 7 dots here in the outermost shell, which is the level 2? Okay. Second thing is this. As far as electrons are concerned, fluorine, notice I used the word fluorine, this is the element, INE, has the capability of gaining 1 more electron because 1, it's a non-metal, so it gains electrons, and 2, it has room for 1 electron specifically right there. And when that happens, it gains an electron, it gives it a net -1 charge. And that now becomes name-wise fluoride. See, that is what you brush your teeth with, fluoride. Sodium fluoride, potassium fluoride, or stannous fluoride. Stannous fluoride is another name for that, is tin. So that is what you're brushing your teeth with. If you're not brushing your teeth with fluorine, it wouldn't work too well. But the fluoride is what's being brushed. And what's happened is the fluorine, one of the reasons it's not monatomic is because it's not very stable sitting there with a empty spot for an electron. So it doubles up with another element, the fluorine, to give us a diatomic. All the diatomic elements that we talked about, by themselves, they can't really be very stable. So they have to double up with another one of themselves so that they fulfill that octet, become stable. Okay. So if that doesn't happen, when they become, gain a full electron, that full electron there's space for it in the 2sp orbit, and now becomes fluoride. And that is true, not just for fluoride. Remember, everybody in the same group, everybody in group 7, that is what's happening to them. Okay. If I move into oxygen, like we did earlier, that will pick up two electrons, and nitrogen 3 electrons. All right. So now let us continue across, and we get to neon. And neon has a total of 10 electrons. Okay, so now, just like fluorine just picked up an electron, neon has already, the element neon has 8 electrons in the outermost shell. 6 of them are in the form of P, in the P orbit, and the other 2 are in the S orbit. Okay, now has obtained a very stable configuration. You got that magical 8 has been fulfilled, just like fluorine having that empty spot by picking up an electron becomes fluoride and obtains that magical 8 that neon has. All right. Now you go all the way around, and the next one would be sodium. So sodium is in the third period, and sodium is in group 1 and has 1 valence electron, just like lithium did when we first started here. Lithium was right here. This is where lithium was, and you see how what they share, 1 valence electron. The only difference is lithium had it in the 2nd energy level, and sodium has it in the 3rd energy level. And if we continue with this thing, if we went all the way around, that would be potassium. Potassium would be in the 4th energy level. Its valence electron, 1 electron. So that is what continues over and over again. Okay. So let's do one from the periodic table very quickly, using the periodic table. All right. Oh, I can't do that. I'm gonna make sure I tell you this before I proceed. Anyway, these are the mathematical equations that when you plot them, you get this area, 3-dimensional area that shows the probability of an electron being in that given area. Obviously, the lighter areas have a low probability, the darker areas have a greater probability. The problem with the model overall, I don't want to call it a problem, the conflict, I should say, is in one hand, we tell you, okay, the electrons are in very specific energy levels. And then we come back with mathematical equations and talk about a probability. And so, in one moment, it's very specific. The next moment, well, it could or could not be there. It depends. It varies about probability. And then a lot of scientists had trouble with that. Einstein had trouble with this model. Okay. However, right now, to date, this is the best model we have. It doesn't mean that tomorrow it might change. As more data comes out, more is known about nature and matter and how it's put together, the more we fine tune the equation. Okay, so the S orbits are round, so you can see here why you probably got the S lettering for it. They're spheres. The P orbits are what are called dumbbell shaped. Okay, there's 3 of them here, both in the X, Y, and the Z position. Those are the 3 orbits. Okay. We won't show the D. There was a link I used to use. I haven't had a chance to look for a new link to give you images, but if you want to see what they look like, yeah, you can Google show image of D and F orbits. there are some crazy looking orbits there for the D's and the F's. Some of them look like space stations, you know, futuristic space stations. But there are 5 different orbits that represent what the D orbits look like, and there's 7 of the F's, okay? Now, the thing to take away from all that is it's all these different shapes. Another aspect of the model is this, that everything is based on one atom, and that is the hydrogen atom. The hydrogen atom is pretty simple with respect to the interactions of the electron and the nucleus, okay? It doesn't, even the most stable isotope doesn't even have a neutron, it's just simply proton and electron. Well, when you jump up to the next one, helium, you've introduced another proton, you introduce some neutrons, and you also introduce another electron. And now you have to account for the interaction between the electrons, which the mathematics do not do a very good job, in that it makes the equation so sophisticated and complex that it's difficult to solve. And so when that happens, mathematicians, physicists, they go around and they do, they say, well, this interaction is not as great, so we can ignore it. They can truncate their equation and simplify it. You know, it may be true or not, you know, that you can eliminate a little bit, some, you know, 0.1% of some interaction, but maybe not, you know. And we don't have the computer power at this point to be able to solve it. Maybe there is, and they're working on it. But nevertheless, all of this is based on the hydrogen atom. So when they got to higher atoms, basically they said, well, the interaction is not as high, so we can assume that we can truncate this part of it, so forth. Even with that, it does still explain a lot of what we observed. So until something better comes up, this is what we got. All right, so all this comes to writing electron configurations, okay, for the element. Now, we will get into how to write the shorthand, and the previous question asked about using the noble gases. But let's do this first. We did, this is presented here, 1s2, 2s2, 2p2 for carbon. And that is presented for you. You, where'd it go? Where'd it go when I come back? I'm missing something here. Oh, yeah. I thought I went too faster. It sure did. All right. Here is the order of which the orbits are filled, okay? Written here in this diagram, or with the lettering down at the bottom, for 1s, 2s, 2p, 3s, 2p, 4s, etc., etc. You can utilize that, either this tool here to help you out when you are writing the electron configuration, okay? All right, you can do that, or you can use the periodic table. And let me zoom up here a little bit. They were, when the slide was demonstrating carbon. Okay, well, let's say we're asked to do the electron configuration of carbon. You can use the previous slide to fill them up. Okay, that's fine. Or I can just go to the periodic table and very quickly go through a systematic approach in this problem. Find carbon, find the number of electrons, which is given to you right there. All right, no big deal. Second thing to look for, after you find the element, find what energy level it's in. It's in the second energy level. Okay, so at this point where carbon is, all those electrons are full. Same is true with the first energy level. So the very first thing I can do is, since it's in the second energy level, I can write 1s, because I know in the s, in the first energy level, there's only one orbit, and that is the s, and that's it. I know that carbon is in the second energy level, so I can put 2s and 2p. Why do I put the p? Because carbon is part of the p elements, which tells me I'm going to be using the p orbits, okay? The s orbits get full, so because sequentially I'm filling them up, right? So I need to put the 2s and the 2p, okay? Now we fill up the superscripts. And notice that carbon is in the second column of the p element. So second column, remember, starting from right here, that's P1, and going across, I go P1, P2, P3. It's in the second column, so I go P2. Okay. I know there's 6 total of electrons. I just took care of 2. I got 4 to go. So I just fill in the rest because those guys, the ones, the 1s and 2s, they're full. They get filled up first. And the maximum s's is 2 max on both of them. So I'm done. So the electron configuration for carbon is 1s2, 2s2, that's superscript, 2p4, okay? Ask yourself, how many valence electrons does carbon have? It is in group 4a, so carbon should have 4 valence electrons, which are denoted by the 2 energy levels, second energy level. And yes, there's 2 in the p, 2 in the s, for a total of 4. So that's consistent, okay? All right, let's do this, and then we introduce the shorthand. Let's do one more. Let's do sodium. Okay. Note the sodium has 11 electrons, so we have to account for 11 electrons. All right. Notice after that, we find out, determine that sodium's in the 3rd energy level, and it is an S element, and it is in the first column of the S element. So guess what? I can very quickly write 3s1. Bam, there it is for the outermost shell. Everything else, the 1 and 2 are full. 1s2, 2s2, 2p6. Right? And so I got 11 electrons total. Of those 11 electrons, one electron is my valence electron in the valence shell, which, you know, it's in group 1a, that is consistent with having 3s1, 1 valence electron, okay? And that valence electron is in the 3rd energy level, and it's in the first column of the S element, so it's 3s2. Okay. Now this is where you can do the shorthand. Is this. We know that the previous, make sure everybody's out. Look where sodium is, and the previous element for sodium is number 10, which is neon. Okay. Previous noble gas. I mean, element number 11. The previous noble gas is number 10, which is neon. Okay. So I can take neon, write the letter symbol, and then put a bracket. What that tells you is the neon in a bracket represents this electron configuration, because by itself, that is electron configuration of neon. So then we can write the 3s1 right after the bracket, 3s1. So this is the shorthand. Okay, and this is probably what you see a lot in the videos that you've seen when they're writing the noble gas in the bracket, and that's just simply the shorthand. So to answer your question, can we do this shorthand? My answer, it depends. If the question says do not use shorthand, then obviously you're going to do a longhand, which is the top one here. If it doesn't say don't use shorthand, then by all means, feel free to use the shorthand configuration for the electron configuration. Okay, for example, let me clear this up. If we look at potassium, number 19, what you do is find the noble gas before it, okay? Noble gas before potassium, number 19 is number 18, which is argon. So you can say argon in the bracket. Okay, we're doing potassium here, this one right here. Potassium is in the 4th energy level, and it's in the first column of the S elements. So it's 4s1. It's in period number 1a, which tells you there's one valence electron, which is in the 4s1 orbit. Okay, so there it is very quickly. If you needed calcium, the one right next to it, just change that 1 to 2. Okay, change that 1 to 2. Now, this is where the configuration for the D's may be a little confused. It only occurs when you get into the D. Remember, these are the D elements. Now, for our purposes, this is 3D1 all the way across to 3D10, 7 columns. Now, you would think that starting, if you had to do number 21, that the D's, because number 21 is in the 4th energy level, you would think that that would be 4D1, but it's not, okay? When you get to the D elements, subtract 1 from the energy level it's in, level. Okay, for D's. So take that 4 and subtract 1, so it becomes 3D1 for number 21. For number 19, that'll be 4D1. For number 57, that'll be 5D1, et cetera, okay? For the F's, find the period it's in. Let's say this is, let's say this is the one you're looking at. So this is 4F1. So for the F elements, subtract 1 from the period it's in, and that is the energy level of that F orbit. Subtract 2, I should say. For the D, subtract 1. Okay, and that is why when you start talking about the D level, how many orbits you can have. Well, you can have the S orbits, the P orbits, and the D orbits get introduced there because they're coming from the elements that are in the 4th period. Okay, 1 energy, and that's due to the mathematics of all that. So that's why you see that sequence. But other than that, you don't have to worry about the D orbits until you get to that element. If we are talking calcium, number 20, there's no D. There's no F. You just don't fill. Those are not even, you don't even have to write them. You only write these levels and orbits of the number you need to get to. Okay. All right, so that's using their label or the periodic table. Okay, and we just did carbon, so 1s2, 2s2, 2p4, 2p2. Okay, again, just to refresh your memory of the order that they're being filled out. And this again represents what I call the S elements, the D elements, the P elements, and the F elements to help you out with respect to electron configurations. So, if you have to be able to write the electron configuration for at least the first 20 elements, would you be doing the D elements or the F elements? Not necessarily. But would you be asked questions about the energy levels of the D's and the S? That's a good chance. Okay. All right. So we have sodium, which is what we do. If you find sodium, find it on the periodic table there. You can use the product table, help you out. It is in the third energy level. Okay, so it's 3s1 to the first column, so its valence shell is 3s1, and then the rest of the ones inside are full. Okay, which brings me to the point. Give this some thought. Okay, that's the electron configuration for sodium. Its outermost electron is in the s orbit. See, notice something. The s orbit, sometimes people have trouble. Why do metals want to lose electrons? Think in the third energy level. We have 3s, the 3p, and the 3d. If you remember, it has the capability of having, what, 18 electrons, right? Excuse me, total. Okay, so here we got an element that has one of the 18. So there's 17 more electrons that it can put in. Okay? But from an energy perspective, it is not very energetically favored to try to slap in 17 more electrons into this thing. Okay, because there's only one electron in the third energy level. And so it would rather lose that electron than pick up any more electrons. Okay. And second of all, it is a metal. Sodium is a metal. And as I stated, all metals lose electrons. And when it does that, let's say, for example, that sodium, that's electron configuration. Right now, sodium element has a zero charge because it has an equal number of protons and an equal number of electrons, equal negatives, equal positives. If I lose one electron, specifically this guy, what charge do you think would be the result?
Positive.
Exactly. And that is what we call ions, okay? That is what you put on your French fries, the sodium ion. That is an element that had lost that electron, okay? And now, I should put a plus here. It has the electron configuration. Who does that look like? What element has?
Oxygen?
No. What element?
Neon.
Neon. This looks like neon, okay? As far as the electron configuration, it is not neon, but keep in mind that I didn't say by losing one electron, it becomes neon. What I said was by losing one electron, sodium now has the electron configuration of neon. Neon is a noble gas. It is stable. Why? Because it's got 8 electrons around it, okay? And it becomes, we use the term isoelectronic. And so in this case, sodium ion is isoelectronic with neon. And they share the same number of electrons and they share the stability. Sodium metal, this one, is not stable at all. When we use it, to use it, we have to actually store it in mineral oil because it's not very reactive with mineral oil. If you were to take a chunk of sodium metal and just throw it into water, it would literally explode because it reacts violently with water. And it gives off a lot of hydrogen and heat and actually ignites the hydrogen. And that is because sodium just dying to get rid of that one electron. And not only sodium, but everybody in that same group. Everybody in that same group is dying to let that happen. So you can see the driving force in nature is to get that magical 8. That's why metals want to lose electrons and nonmetals like oxygen want to gain. That is the electron configuration of oxygen. All right, it is a nonmetal. It has the capability of gaining electrons because being a nonmetal. How many electrons do you think oxygen will gain?
2.
2, exactly. It will pick up 2 because it has room for 2. And when it does that, it fills that 2p orbit and you end up with a charge. Anybody want to take a guess of what that charge will be?
It's
you gain 2 electrons, what you
a
lose,
negative charge.
-2 charge. You got to give it a magnitude. Because
Uh,
you can gain and lose. You can gain or lose, for example, a -1, a -2, a -3. Nitrogen, being where it's at, will gain 3 electrons, ends up with a -3. Oxygen will gain 2 electrons, becomes a -2. And fluoride, it's in that group of 1, will gain 1 electron, be a -1. Okay. And now the thing to remember, because we start talking about name and nomenclature, oxygen, elemental oxygen is oxygen. But when it becomes an ion by gaining electrons, we change the name to oxide. Remember fluoride? It came from fluorine. Chloride, coming from chlorine, IDE. The chlorine became chloride when it gained 1 electron. The fluorine became fluoride. Oxygen became oxide. Okay. The nonmetals, when they become ions and gain electrons, we have to change the name. The metals, name stays the same. Sodium is sodium, be it an ion or an element. Okay. And that's the introduction of the beginning introduction of nomenclature and naming, so we can make sodium oxide. It wouldn't be a sodium oxygen. It would be sodium oxide, sodium chloride, potassium chloride, so on and so forth. Here we go with calcium. Okay. Calcium, 1s2, 2s2, 2p6, and 3s2. Okay, so the third energy level, it is in group 2. It's got 2 valence electrons. It is a non-metal. It's a metal. I almost said non-metal. It is a metal. It would lose electrons and specifically lose these 2 out here, just like sodium does, and becomes a +2 ion. And that is what you're ingesting when you're taking calcium, vitamins. You're ingesting calcium +2. Not calcium by itself. Okay, not the elemental calcium. All right. Again, the driving force by just like sodium did. Guess what happens? Look at what's left in the innermost shell. In this case, when both sodium and calcium lose those valence electrons, they become isoelectronic with neon. Again, the driving force to become like a noble gas. So it become with 8 electrons around it and become more stable. Now let's see if you can deduce something else. Okay,
I got a question real quick.
Sure.
Sorry. Is calcium in the 4th energy level?
Yeah, right here. No, it's 1, 2, 3, and what am I doing? Yeah, there it is. What's missing? Oh,
So should it be 4s or?
we're still missing the 3s. We're missing a lot here. Thank you very much. Let's fix it. Can you guys see where the problem is? Let's do this. Okay, that's a big typo there. So we got 1, 2, 3, and 4, and here's calcium. And so it should be 3s, all this, and then 3p6, and then 4s2. You see that? It filled up all this first energy level. The second, the third is full because when it becomes it be argon to become isoelectronic with argon. So I got to fix that. That's a good catch.
Yeah, I was just asking.
No. Yeah, that's a very good catch. Let's do. I wonder why it's not there. It is right there. You see it? For some reason, it's not showing when I go into that. There it is. Okay, my animation got stuck. It's clear. Okay, there we go. Is that more sound more logical?
Yeah, good to go.
Yeah, yeah, good to go. And then what happens, like sodium losing that electron, calcium will lose this. And now this is isoelectronic with argon. Okay, by losing 2 electrons. And again, we got 8 valence electrons. So calcium becomes a calcium plus 2. Okay. All right. Clear. Then we have chlorine, which is again 1s2, 2s, 2s2, 2p6, 2s2, 2p5. Okay. Chlorine, as the case with oxygen, has the capability of gaining 1 electron because it's got 1 spot empty there in the p orbit. Okay. And so it can make this 6 and it becomes a negative charge. And this becomes chloride. Okay. And this one up here gained a -2, gained 2 electrons, and this became oxide. So the nonmetals, which is this one and this one, gain electrons to fulfill the outermost shell, whereas the metals lost electrons, so that 2,3s1 electron went away, giving me a plus charge, and the 4s2 was lost to give me a +2 for calcium, okay? And in all cases, in doing that, now we have a octet around the new ion, and now a lot more stable, okay? A lot more stable than by themselves with the full electrons on there and driving again to get to the octet. Now, what does your intuition tell you? If, for example, let's clear that. Let's take sodium. Okay. Sodium has 3 energy levels. Okay. So it has a specific radius from the 3rd energy level to the nucleus. Okay. Now, in the process of losing the electron, that 3rd energy level now is empty. There's no electron, and it becomes a positive. You suspect that the new radius is smaller than the original radius, or is it the same for the sodium ion? When I comparing the sodium element with the sodium ion, which one would you anticipate to have a smaller radius? The ion?
The ion.
The ion, exactly. Because this 3rd energy level is no longer there. So the next one that's full goes to the 2nd, so it's shrunk. On the converse is when the nonmetals pick up an electron, and now this guy picked up 2 to give us a -2. It's gaining 2 negative charged species. There's 4 of them in that p orbit, so I'm putting 2 more in there, negative charge. So these are going to want to repel from each other because they're negative. And so the radius of the ion in that case gets bigger, okay, in gaining electrons. So the radius of the nonmetal ion would be larger than its respective element. The radius of the metal ion would be smaller than its respective element, okay? All because it lost and gained electrons. All right. So this kind of shows it all with respect to the electron configuration as you go through each particular element. Now, for us here in Chem 130, remember I mentioned D1 shoots across to D10, and starting here, F1 shoots across to F14. Okay, sequentially, D1, D2, etc. You can see here that in reality, that's not the case. You can see some of them depends on the multiple things. They stay at the same number. Some jump, go from an 8 to a 10. That's beyond the scope again for this class. We'll just keep it sequentially, D1 to D10. The same is true for the S. It goes from F1 to F3. Okay, but we're going to just keep it sequentially, F1, F2, F3. It has to do a lot with the interactions of these electrons with other orbits in there. That sometimes is a lot more energetically favored to go into another orbit than to do the sequential thing. But the rest of them, you know, this element here, 2s2, okay? Notice the ones in the same group, okay? They share the same number of valence electrons. And those valence electrons are also sharing the same type of orbital. Where they differ is the size of that orbital. Energy level 2 is much smaller than 3, 4, 5, etc. Which should tell you something else, that as far as the radius of the elements, this element here is much bigger radius-wise than this element here. Because, you know, going down the periodic table, we are increasing our energy level. So we're getting a bigger onion, if you will. We got a small onion up in energy level 2. And as we go down the periodic table, the radius of the elements get bigger. Okay. All right. Tell you what, let's I'm supposed to, what time did I say? 6:40? 1 to, what did I say? Wow, 4 to 5, and then 5 to 6.
I think your email said 4 to 6:40.
Yeah. Yeah. Well, let's take a 10-minute, then we'll come back.
Okay, Roger.
Thank you. Be right back. All right. So we have this table here that shows you the electron configuration for all the elements. Okay, so use either one, use the periodic table to figure it out, or use this equation down here at the bottom, whichever works out. Now, as I mentioned, the noble gases, the driving force, I introduced it, is to get to that magical 8, because we know that noble gases are very stable. Whether they're happy or not, I don't know. He used the word happy, but their outermost shell is full, and they have the octet rule has been fulfilled, except for helium. Helium has their own rules for the duet. Okay, so electrons, the valence electrons, very crucial in chemistry. That's where all the action happens. That's where all the process happens. It doesn't happen with the electrons in the core, what are called the core electrons. Okay, core electrons are the ones inside. They're full. There's no room for them to pull out or to add more to them. Okay, more electrons. So if you look at phosphorus, here's the electron configuration of phosphorus: 1s2, 2s2, 2p6. What's denoted in red is the core electrons. The outermost shell, the valence electrons, are in the third energy level, where we got 3s2, 3p6. You can see that phosphorus, based on its position in the periodic table, is in group Roman numeral 5, which tells you that there are 5 valence electrons for phosphorus, just like nitrogen. Okay, here's the valence electrons. Now, phosphorus is a non-metal, and therefore will gain 3 electrons because it has room for them right here. And when it does that, it now becomes the -3 because it will pick up 3 electrons with a -3 charge. And we also change its name to phosphide, IDE. Notice the common factor is the IDE, phosphide, chloride, oxide, nitride, oxide. You know, that is a key, the IDE, to tell you we're dealing with the single element. Because down the road, you're going to be hearing things like phosphate, ATE, phosphite, ITE, totally different from phosphide, IDE. Okay. Totally different. All right, so that's just a word about valence electrons. Here, the question is this, okay, how many valence electrons do they have? Well, you can write out the electron configuration, or you can find its position on the periodic table. You'll see that chlorine is in group 7. That tells you there are 7 valence electrons. Of those 7 valence electrons, which are denoted right here, 2 of them are in the s orbit and 5 of them are in the p orbit. Chlorine has the capability has room for 1 more electron. It's a nonmetal. It will pick up 1 electron and put it in the 3p6 orbital and become a -1 charge. Beryllium, its configuration is 1s2, 2s2. It has 2 valence electrons. It's in group 2. Aluminum is in group 3. Okay, so you can see here that its electron configuration is given as 3 for the valence electrons, 3s2, 3p1. There's 3 valence electrons. 2 of the electrons are in the s orbit of 3 energy level, and the other one's in the first in p1. Okay, it is a metal, so aluminum will lose electrons. Just the fact that it is a metal, and it will lose specifically 3 electrons. So it ends up with the +3 charge. Notice the trend here. We've been talking about ions, elements losing electrons. You know, we had sodium with the +1 charge. We had calcium with the +2 charge. Okay, so the magnitude of loss and gain electrons can be as little as 1 electron, like to give you a +1, or 3, losing 3 electrons, like in aluminum, to give you a +3. And the same is true with the, nonmetals, that you can either gain 1 electron for a -1, or as much as 3 electrons for a -3 charge. The number it needs depends on what it needs to lose or gain to fulfill the octet, to get the magical 8, if you will. Okay. All right. So the Roman numerals tells you the valence electrons. Okay. With the exception of helium, which always will have 2. Okay, but all the other noble gases in group 7 and 8A all have 8 valence electrons. All right, so from group 1A to 8A, it's given there. How many valence electrons for SR strontium? We find it on the periodic table. It is in group 2, hence it has 2 valence electrons. Bromine is in group 7, has 7 valence electrons. Argon is a noble gas, and stable, very stable, and therefore has 8, being in group 8. Silicon, like carbon, is in group 4, so it has 4 valence electrons. And sulfur, like oxygen, has 6 valence electrons. Okay, the thing to remember here is don't confuse total electrons with valence electrons. Valence is the number of electrons in the outermost energy shell, which can be from energy level 1 through energy level 7, outermost. All right, so the driving force that I've been talking about is trying to have an electron configuration like a noble gas, trying to get that magical 8 number. And atoms will either gain or lose electrons to obtain that magical 8, okay? And when that occurs, we form ions. Right now, that's the general term, ions. Those either is positive or negative, they're called ions. We're going to give them specific names at a later date. Okay. Now, we have sodium. We talked at length about this. Sodium has 11 protons. Okay. 11 protons. So the electron configuration is 1s2, 2s2, 2p6, 3s1. Okay. So it has 11 protons, 11 electrons, 11 positives, 11 negatives. So you get a net 0. The sodium ion, being in group 1, will lose that 1 valence electron. And now it still has 11 protons. Okay. It wouldn't lose protons. If it loses protons, we've made another element. Okay. But now it has 10 electrons. So we got 11 positives, 10 negatives for a net charge of a +1 charge. And now its electron configuration is like neon, okay? It did not become neon, but it shares the same number of electrons as neon. Now go to the other end of the periodic table, we look at sulfur, okay? Sulfur, its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. Okay. It is a nonmetal. You can see here that based on the valence shell, it can gain 2 electrons. So it's got, at this point, as an element, 16 protons, 16 electrons, net 0 as the element. As it picks up electrons, it's going to pick up 2, specifically 2. So now it still has 16 protons, but now has 18 electrons or 18 negatives. 16 positives, 18 negatives. Its overall charge is a -2. And hence we put a superscript -2 on the elemental symbol for sulfur, as we did put a positive, superscript positive for sodium in the previous example.
So I got a question
Sure,
about that
go,
for the
go.
positive and negative. When you are talking about a charged ion like sulfur right here,
Yeah.
is the negative always after the number? Does that matter?
Like either, oh, I see, okay. Whether you're saying, I mean, -2 versus 2 negative,
Yeah, exactly.
makes no difference.
Okay.
It's the
All right.
same thing, yeah.
All right. Thank you.
Sure, no problem. Yeah, I had a conversation with a colleague about that. I'm like, you put 2 negative, but -2 is the same thing. I guess he had a problem with that, but to me, it's the same thing. All right, so in fact, a lot of times what I do is when you'll see me do this a lot. Let's say sodium, I put a circle around the charge. Okay, like -2, I put a circle, and it's just to show that it's a charge, and it's just my way of doing it. Whether you put a circle there makes no difference. So I just be noted. Sometimes if you're writing a lot of equations and so forth, your charges get lost, and the circle kind of keeps track of it for me. All right, so now everybody here by gaining or losing electron is now isoelectronic with a noble gas. Which one they are depends on where they are in the periodic table. You'll see the trend for metals. When they lose electrons, they become isoelectronic with the noble gas behind it. Okay, so sodium with 11 proton electrons now becomes an ion, now has 10. So that's the metal, that is element number 10 behind the neon gas. Whereas sulfur, by gaining 2 electrons, excuse me, is now noble, is isoelectronic with noble gas in front of it. Okay, it's the driving force. So for metals, there's a noble gas behind it. For non-metals, it is a noble gas in front of it, as far as how many electrons it's striving to get. A lot of students see this and they don't read the question carefully, because if you look at the image you're talking about, you got potassium, and then it's a +1. So that is the ion. So you got to be careful that you're answering the question for the ion and not for the element itself. Okay. And so if you do the electron configuration, you should get 1s2, 2s2, 2p6, 3s2, 3p6. What happens is many students write 4s1. Well, that can't be the case, because if it was potassium element itself, then that would be correct. Okay. But that's not the case, because the question says the ion. Notice how the ion now is isoelectronic with argon. Nitrogen gained 3 electrons, so now it becomes nitride. That's one takeaway from this. Before, when it was just N, it's simply nitrogen. Okay, that's the element. But when it gained 3 electrons, it becomes nitride. Okay, nitride. And for example, we're going to get learn how to write formulas. So we will write a formula like K subscript 3 N. That is potassium nitride. It would be incorrect to say potassium nitrogen, because this is the nitride ion. Okay? So naming it correctly is important, because sometimes you're given the name and need to write the formula. And you got to be aware of nitride, and that tells you, okay, I'm dealing with a -3 charge. And then down the road, we're going to talk about nitrate and nitrite, ITE. See, totally different species, but sound very close, right? So we got nitrogen, nitrite, nitrate, and nitride. All right, so magnesium has the magnesium ion has the electron configuration of neon. 1s2, 2s2, 2p6. Again, in both cases, look at the valence shell. The valence shell for the potassium ion has 8 valence electrons. 8, magical 8. The valence shell for nitride also has 8. And for the magnesium ion, also has 8. The driving force being a negative charge or a positive charge ion is to get to that 8. Okay. We need to learn to make sure we know what charge that it would have. For example, you could be asked the question, all right, I'm dealing with, we did a calcium, and the question is, well, we need to know what the ion charge will be. Well, we find calcium on the periodic table and realize that it is in a group 2A. Group 2A means there's 2 valence electrons, so that when it comes ion, we get a +2 charge. And that's important, because we need to know the ion, because we're going to start combining these positive ions with the negative ions to make compounds, okay? To make compounds. And then once we make the compounds, we're going to react compounds with each other to write a chemical reaction. Okay, right now, we're still kind of dealing with the alphabet of chemistry, but we're getting a little more sophisticated than just letters now, talking about ions. All right, so This has to do, this section deals with the charge, which I've talked at length about, but just another emphasis, because we need to know what kind of charge they have, because we need to know how to put them together when we write compounds, okay? So everybody in group 1, which brings us to a point, okay? And let me pull up. Right. Now, everybody in group 2, 1 and 2 will always have a specific charge. Everybody in group 1, excluding hydrogen, notice in that box I did not put hydrogen in there. Hydrogen does have a positive charge, but it can give you a negative charge. So, and it's not a metal, so that's why hydrogen is not included in this. But everybody in group 1 that's a metal will always have a +1, okay? And then everybody in group 2 that's a metal, which is all of them, will always have a +2 ionic charge. Okay, so we got 1, 2, 3, 4, 5, 6. We have 12 examples of elements that have, there's 12 here, that we know 100% of the time what their particular charge will be when they become ions. And then we add 4 more that are always 100%, and those are circled. I got aluminum here, and then zinc, and then we go on that angle to the left, zinc followed by Ag, which is silver, and then we kind of make a right turn there, go back to Cd, that's cadmium, okay? That kind of shape to help you remember you got aluminum, kind of go like this, and it helps you remember which 4 of these. So there's 4 more, okay, elements that always have a consistent charge. For example, aluminum will always have a +3. Zinc will always have a +2. Silver will always have a +1, and cadmium always have a +2. So we have a total of 16 metals that their charge, their ionic charge, is always known 100%. And that's important because we know what kind of, when we start learning to write names for these compound mixtures that we start putting together, we need to know that because that tells us whether to put what we call a Roman numeral in the name. What does that mean for everybody else? Everybody else in here that are metals, their charge can vary. For example, copper under certain conditions can have a +2 charge, or it can have a +1 charge. So notice something, it's a little bit ambiguous. We got copper 0, which is the elemental copper. Now I got copper +1, which is ionic copper, but with a +1 charge because it lost 1 electron. Then you also have copper +2. Okay, so you got 3 forms of copper. Well, how do you distinguish which one you're talking about? Obviously, if you say copper element of copper, no question there is copper 0. But the other copper 1 and copper 2, how we distinguish them is we use the Roman numeral in parentheses. So copper 1 will be given the name copper, C-O-P-P-R, and then in parentheses, the Roman numeral 1 capitalized, okay? And copper 2 would be Roman numeral 2, 2 I's. Or any other ones, you can get +4, so you put IV. So we use the Roman numerals to tell us what the charge it is, because their charge is variable. Now, when we come to nitrogen and phosphorus, these are nonmetals and therefore will gain electrons, and therefore it's in group 5. So these guys will always have a +3, always. Oxygen, sulfur, selenium, beryllium, okay, always have a +2. Fluorine, chlorine, bromine, iodine, and a little bit AT, but most of these here always have a +1, always 100%, okay? So even now, when we start adding, we start putting these, combining these ions, we always put a negative and a positive together, and we're gonna learn how many of each at a later date here. But you can see here, I can start doing lithium chloride, lithium fluoride, lithium bromide, lithium iodide. Do the same thing with sodium fluoride, sodium chloride, sodium bromide, or sodium oxide, sodium sulfide, sodium selenide, sodium nitrite, sodium phosphide. You see how we start building up? And that's just a couple metals. So you're probably up to 1,800 compounds already when we start mixing and matching. Okay. All right.
So I got a question.
Yeah, sure.
I just want to clarify some things at the top. So for nitrogen, phosphorus, oxygen, sulfur, all the elements that you circled and highlighted and then put the numbers on top, are those negative or
Yes.
positive charges?
They're always they're non-metals.
Okay.
So always gain electrons. Okay.
Gotcha.
So everybody in group 5, remember they're in group 5, so they share 5 valence electrons. They got room for 3. So everybody in group 5 will gain 3 electrons, hence -3 charge. Everybody in group 6, they got 6 valence electrons. They got room for 2. Okay, so they pick up 2 electrons. All the nonmetals in group 7, they got 7 valence electrons. They're striving to get that magical 8, so they only need 1 electron. So everybody in group 7 would have a -1 charge because they all picked up one electron. Okay. All right. The other thing you can get from this is because it has a -3 charge, the additional information says I can make 3 bonds for everybody in group 5. Can only make a maximum 3 bonds and still have a neutral charge. Everybody in group 6 can make 2 bonds and still have a neutral charge. Everybody in group 7 can make 1 bond and still maintain a neutral charge. Okay, so it's telling you that group number tells you how many valence electrons. It also tells you how many electrons it needs to gain, which also tells you the charge the ion will have, and then tells you how many bonds it can make. Okay. So this periodic table, the way it's written, pretty much just a ton of information. All right, so where are we at? All right, so group 1, they're going to be a +1 charge. Group 2 will be a +2 charge. Okay, just the rehash that we just talked about. Group 3, the metals will lose 3 electrons and end up with a +3 ion. Okay. Now, it doesn't make a difference if either you write +1 or 1+ or -1 or 1- makes the same. What's important is that you make sure you put the magnitude and the charge someplace somewhere. It's got to be superscript right. All right, group 6. Okay, they're going to gain electrons. And then, group 7 want to pick up 1 electron. Group 6 want to pick up 2 electrons. Just the rehash of what I just mentioned. And all of these are the nonmetals. Nonmetals want to gain electrons. Okay. Yeah, I'll summarize all this here in a second. So group 7 through 5, here's their respective charge because these are nonmetals. And it's really going to be kind of, if you think about it, when you compare metals versus nonmetals, the metals totally outweigh the number of nonmetals. So ones I've circled right there, or most all the nonmetals that actually do, react and so forth to give you a negative charge. There are not that many compared to the metals, okay? Metals lose electrons, form ions. Now here's the alternative name of the negative charge or the positive charge. When they lose electrons, when metals lose electrons, yes, they become ions, but specifically, they are called cations, okay? And the nonmetals, when they gain electrons, they specifically have a name called anions. Anions. They're both ions, but the term ions is generic. We don't know if it's a positive ion or a negative ion. So they use the term cations for positive and anions for a negative. Okay. And group 4, well, group 4, think of the group number as a fence, and with group 4 being on top of the fence, okay? And so they can either, because they're +4, they got 4 valence electrons, to obtain the magical 8, they can either do one or two things. They can gain 4 electrons, or they can lose those 4 electrons. And it is quite feasible that depending on the reaction conditions. So their charge can vary from a +4 to a -4, depending on the reaction conditions and what's going on. Okay. Obviously, group 8, nothing's going to happen because they're noble gases. So if you look at the charges, so you go across the table, periodic table, for only the A elements, okay? The B elements, as I explained earlier, they vary. I can have a variety of different types of ions for those metals. We cannot predict very well what their charge would be. It depends on the reaction conditions. Now, we'll be able to determine their specific charge because thing to remember here when we start putting compounds together, when we put them together, we have to put enough positives and enough negatives together to equal 0. We're always going to know the charge of one or the other, or both. But if we don't know the charge of both ions we put together, we're going to know the charge of at least one of them, which then allows us to calculate what the charge of the partner is. Because when we put enough positives and negatives together, we have to put them such that they balance each other out. And so if I don't know the positive charge, I would know the negative charge, and I know it's equal to 0. So I can calculate what the positive will be, okay? We'll have some examples of knocking that out. All right, so here, basically they're asking you what is the charge, what it becomes. So step-by solution, 1, identify whether it's a metal or a non-metal. Once you know it's a metal, then you know you're going to lose electrons. Once you know it's a non-metal, it's going to gain electrons. Second step is identify them on the periodic table and identify the group number, because that will tell you whether if it's a metal and loses electrons, it's going to tell you how many it's going to lose. If it's a metal, non-metal and gains electron, that group number will tell us how many electrons it needs to get that out, to get to the 8. So if you look at lithium, lithium's in group 1. And so therefore lithium will lose an electron and become a positive, okay? Positive 1 charge. Magnesium is in group 2. And it's a non-metal. So it's going to, excuse me, nobody was said that. Magnesium is a metal. And it's going to lose those 2 electrons. So it ends up with a positive 2 charge, okay? Sulfur is a non-metal. It is in group 6. It needs, being in group 6, for non-metals, you got to think about this a little bit. For a non-metal, you find the group it's in, and then that tells you how many more electrons it needs to get to the 8. It is in group 6, so it needs 2 electrons to get to the 8. So therefore, it has a negative 2 charge. Okay. Bromine is in group 7. Group's Roman numeral 7. It needs just 1. So it will be a -1 charge. Nitrogen is in group 5. It's a nonmetal. It will gain electrons. Specifically, it will gain 3 because it needs 3 electrons to the 5 it has plus the 3 gives me the 8, right? Which results in a -3 charge. Okay? And then aluminum is in group 3. It is a metal. It will lose those 3 electrons, resulting in a plus 3 charge. Now, an additional thing to remember about this is the name. The metals, specifically lithium, and magnesium, and aluminum, when I want to name lithium, just the elemental lithium, I would say elemental lithium. If it's the ionic lithium, I say ionic lithium. Notice lithium does not change. To determine if it's the element or the ion, you have to say it's an ion. You have to tell what it is. The nonmetals, not so much. The nonmetals, this now becomes, this is sulfur. The name for S, which is elemental sulfur, okay? When it becomes an ion, it becomes, we drop some of the lettering, and after the F, we add IDE, so this becomes sulfide, okay? Bromine is the name of the element. When it becomes the ion, it becomes, name-wise, bromide, okay? Nitrogen, when it becomes the ion, becomes nitride. And then we got aluminum, becomes aluminum ion, okay? That's it. So it is the nonmetals that we change the name. If it's just the single element itself, then it becomes sulfide. And this is why I'm saying you got to be very careful here, because we got sulfur for S, okay? We just talked about -2 ion. Its name becomes sulfide, okay? But we also have, when sulfur, the ionic sulfur combines with oxygen, we have sulfur combined with 4 oxygens. It also has a -2. And guess what its name is? Sulfate. Okay. And that's when it's combined with 4 oxygens. When it's combined with only 3 oxygens, it still has a -2 charge. It becomes sulfides. Now, if you look at the periodic table, you'll see a little table on the left side that deals with polyatomic ions. You'll find those 2 in there, okay? And so we got to be careful with the language, because it's very specific, okay? Very specific, because now, notice we got lithium. We can combine lithium and make lithium sulfide, or lithium bromide, or lithium nitride. We can do the same thing with magnesium, magnesium sulfide, magnesium bromide, magnesium nitride, etc., etc. We're building up our database with respect to naming, because recall that we have that nomenclature exam, which, even though the due date is not till the end of the semester, you really you may want to go in there and do the test and see where you're at. Okay, give you an idea of what they're looking for, and help you, assist you to determine, well, what points do I need to practice and do more of. Okay, in nomenclature, we do have a full chapter in nomenclature, but I'm always trying to bring that along as we progress with learning more about chemistry. We take the time and mention about nomenclature and naming. Okay, I've already mentioned what isoelectronic means. Is basically trying to have the same number of ions. Isoelectronic, iso meaning same, electronic, electrons. Okay, you may be asked the question, for example, what atom is isoelectronic with magnesium? Well, to answer that, you have to write the electron configuration for the magnesium ion, or magnesium cation could be stated that way. Okay. And once you do that, it becomes 1s2, 2s2, 2p6, okay, which is neon. Phosphorus, and the quickest way to do this is you can write the electron configuration, okay, or find, if it's a non-metal, find the metal, and then go back to the element, the noble gas that's behind it. Here's magnesium. Okay, number 12. Well, the noble gas behind it is number 10, neon. Okay, phosphorus is coming up. It's right here. It's a non-metal. It's going to go forward. So it's isoelectronic. Phosphide is isoelectronic with argon. Okay, so you don't really have to do the electron configuration, just find its position. Like, for example, someone is asked what's the bromide ion is isoelectronic with who? Well, we got to find bromine. We can see it needs one more electron to become isoelectronic with Kr, which is krypton. Okay. Okay. Lithium will be isoelectronic with helium, and hydrogen eventually will become helium when it gains some stuff. All right, let me erase some of this. And I think we're going to be pretty close to finishing up this chapter. Okay, so argon. All right, so you may get a table like as follows, and then they're asking you to write the electron configuration. Be aware of whether it's an ion or the element. Okay, in our cases, all four of them are an ion, so make sure you write the correct electron configuration. Notice that when it comes to ions, the electron configuration for all of them in its valence shell would have 8 electrons. So calcium plus 2 has 8 valence electrons in the third energy level. Oxide has 8 in the second energy level. Chloride, 8 in the third energy level. And aluminum has 8 electrons in the second energy level. Okay. So that means that the calcium ion is isoelectronic with argon, oxide is with neon, chloride is with argon, and aluminum is with neon, okay? The key takeaway here is this. The ions did not become calcium, did not become argon. That's very important. Calcium ion became isoelectronic with argon, meaning that they share the same number of electrons. But being that argon, that would be totally 100% incorrect. Okay, so in this case, we got another table, and I think this is the last chapter. So what they've done here is they're giving you 2 metals, selenium and aluminum. Nope, non-metal, excuse me. Right, regardless of what it is, yeah. They give you 2 different elements. One happens to be an anion, which is Sc, -2, and the other one is a cation, which is aluminum with a +3 charge. Now they're asking you to calculate and determine the number of protons. From that, determine the number of electrons and determine the number of neutrons. Remember that that number on the far uppercase left is the mass number. And so taking that number, subtracting the atomic number will give you the number of neutrons, okay? So for Se-78, it has 34 protons, 34 electrons, and there are 44 neutrons. Notice 34 plus 44 equals 78, okay? Now, it has a -2 charge, which tells you that Se is in group 6, and it is. It's underneath sulfur. Okay. And therefore, it's a nonmetal, therefore it will gain 2 electrons and it has a negative charge. So yes, it has 34 protons, hasn't changed from the element. It has now 36 electrons because it picked up 2 electrons. And the neutrons remain the same, okay? So way back when I stated you can lose neutrons, lose electrons all day long. It's not going to change what that element is until such time you lose or gain a proton, then you've made a whole new species. Aluminum, okay, has 13 protons and 13 electrons when it is neutral, and it has 14 neutrons. It is a metal. It is in group 3 and we lose 3 electrons, and therefore now it still has 13 protons, but now it lost 3 electrons, and now has a total of 10, and nothing's happened to the neutrons. All right, so doing this table, just be careful, read the formula correctly, so make sure that you are dealing